The purpose of this video is to cover goal 3 of integral applications. You can read the goal. It says be able to use the mean value theorem for integrals to find the average value of a function. As I mentioned before, there were 4 big theorems in AP Calculus, and this is the last of the 4. We've talked about the intermediate value theorem, the mean value theorem. Now that was for derivatives. It's just called the mean value theorem. This one is referred to as the mean value theorem for integrals, so make sure that you know that this is different from that other one we talked about. So we had the intermediate value theorem, the regular mean value theorem, the extreme value theorem, and now this is the last of the big 4 theorems that they test. So this is the mean value theorem for integrals. Its big usage is for finding the average value of a function. Now, I'm going to split this into 2 videos. One, I'm going to give the concept of the mean value theorem and how that works. But its major application is in finding the average value of a function. So you can think about a function having inputs and outputs. A lot of functions have lots of outputs. In fact, a smooth continuous function has infinite outputs. Say you wanted to know the average of those outputs. So, for example, maybe you have a bank account or stock or something. Right now the stocks aren't doing so well, but say you had some kind of equation that modeled the behavior of those things. You could actually find its average value. So I'll give you some examples of finding average value in the second part. But this first video is basically about the theory of finding, fulfilling the mean value theorem for integrals. And then once we understand that, we could see its application to find the average value of a function. So let me give you the concept of this mean value theorem for integrals. And then the next video will tell you how it finds average value for a function. All right, so it's always good to have some kind of visual example to wrap your head around. So this is just a picture of a function. You can see up in the corner it says f of x equals 2x cubed minus 2x squared minus 6x plus 10. So it's your typical cubic polynomial. And there's an interval from a to b. The picture I found at a to b, I mean, those are usually numbers. It could be like 1 to 4 or 17 to 500, whatever. So we know that the integral from a to b of f of x dx, if you integrate from a to b of this thing, it gives you the area under this curve. It gives you this sort of light blue shade area in the picture. Now, the mean value theorem for integrals works on a concept that this is all curvy. It sort of thinks, what if the function were all level? What if it were straightened out? So the way I try to think of it is, think of this as like a piece of ice or something, like it's frozen in place. So almost like you're in like an aquarium or something. And somehow the water got frozen like this, where it's higher in one spot, lower in the other spot. If you thought about leaving this sort of piece of ice out, this like sheet that has this weird shape, leave it upright, and give it a few hours to melt, and what would happen is this frozen shape, the water would melt in the tank and it would kind of level out. So the mean value theorem for integrals talks about that value, that level value. So let me show you a picture, because normally I would draw on this, but I don't have my smart board. So on this whiteboard in the back, I redrew the picture. And so the idea of the mean value theorem for integrals goes as follows. It's one of those existence theorems. It doesn't tell us where this happens, but it basically says that on the interval, there's a place where what I'm about to explain does happen. So if you pretended the blue melted and sort of flattened itself out, you'd get that red curve, and that's just my best guess of about where that would be. But you could imagine that if that was like water, it would level out, and the equation below would be true, that basically there's some area under the blue, which is represented by the integral from a to b of f of x dx. The red also has an area. Now, it has the same area as the blue. If you think about that as like amount of water, the amount of water wouldn't change. It would just kind of flatten out. So the area under the red line will have the same area. So what the mean value theorem for integrals says is that such a spot exists where this spot here, x star, that basically, since this is flattened out and made a rectangle, you get that rectangle, so the area of that rectangle would be its base times its height. So that's what this is representing. So basically, there's this red line where the area under the red line is equal to the area under the blue curve. Now, the mean value theorem, now this is kind of maybe obvious that there is some spot where you would get equal areas. The mean value theorem states that there has to be some x star on the interval where when you take the height of the x star and multiply it times the base, basically finding the area of this rectangle, that there must be a spot like this. There must be a spot on the function that if you make the horizontal line there, the area of that rectangle will match the area under that curve. So hopefully that makes some kind of sense. So this is referred to as the mean value theorem for integrals. Once again, it states that there must exist at least one spot, this x star, where if you take its height times its width, you'll get the area of this rectangle. The area of that rectangle must match the area under the curve. So it's basically a way of getting a rectangle that matches your integral, and that spot has to exist. Now, there could be more than one spot that fulfills this. In my picture, there's really only one spot. This is x star. There's f of x star. But there might be other spots on here depending on the curve where it hits that height several times. The bottom line is that the theorem says that spot, there must at least be one spot. So there's at least one. There could be multiples. The theorem doesn't find the value for us. So what is that x star on that interval? I know it's between A and B, but I don't know exactly where. Now, the example I'll do is it's not difficult to find a lot of times, but realize the theorem doesn't tell you how to find it or what it is. It just says that it exists. So we've seen this before in some of the other theorems that we've done, that there's this existence of something. So there's the existence of an x star on AB, where if you build this rectangle out of the height of x star, the rectangle will match the integral value. So let's plop this back up. So that's the concept. So hopefully now when I show you the theorem, you'll get some idea. So this is the mean value theorem for integrals. It states, let's see if I can get this all on the screen here. There we go. It states that if f is continuous, clearly the function, you don't want it to have any crazy breaks or any weird behavior like asymptotes or anything in it. So like most things in calculus, if this is a continuous function on the closed interval AB, then there exists at least one spot that we're going to call x star that is on AB such that this equation is true. That if you take the integral from A to B of the function, which is that area under the curve, there will be a spot on the interval that if you take its height times the width of the interval, that's the rectangle part, that they'll be equal. All right. So this is the mean value theorem for integrals. And this equation needs to be fulfilled. So most of the time we're going to use the concept to do something called average value. But like I said, I'll do that in the next video. I want to show one example of just purely doing a problem about the mean value theorem. So here's an example of finding that x star. So given f of x equals x squared, just pick the simple squared function for the example. It wants me to find the special spot, x star, on that interval 1, 4 that satisfies the mean value theorem for integrals. So I'm looking for that x star. It's got to be between 1 and 4. And the property that x star needs to have is that if I do the height at this spot times the width of that interval, it should equal the integral of this on that same interval. So the area of the rectangle formed will be the area that's under that curve. Okay, so before you do this, now I didn't show it on the example, but you should check that the conditions are met. make sure that it is a continuous function. So I picked x squared. X squared is continuous on 1, 4. Even if the function has discontinuities, if it's continuous on the interval, you're fine. So x squared is continuous everywhere, so I don't need to worry. But in case it did have some discontinuity, I would only run into a problem if the discontinuity were on the interval I was talking about. So in this case, x squared is completely continuous, so it's certainly continuous on the interval 1, 4. So the theorem states that there must be this spot, and I'm going to show you how to find the spot for this using the formula. But I'm going to find some x star that has the property that I mentioned before, all right? So I'm going to swap out boards here and show you the work for this. All right. So let's move the screen out of the way. So back here is the work. I sort of rewrote the problem at the top. So the top just has my f of x is x squared. I'm on 1, 4, and I'm looking to find the x star that satisfies the mean value theorem for integrals. So I'm going to use that formula I showed you on the slide. Basically, the mathematical formulation of the mean value theorem for integrals is written on the top. It says that the integral from a to b of f of x dx, once the conditions are met, there must be an x star where it's equal to f of x star times b minus a. Now, since I verified the conditions, there must be some x star that fulfills this. So in the next line, I start filling in the specific information for the problem. So in the next line, my interval's from 1 to 4. X squared is my function. So basically, the area under x squared from 1 to 4 has to equal some f of x star. Now, that's what I'm looking for. F of x star, since the function squares things, just turns out as x star squared. So I don't know what that quantity is. I'm going to find it. B minus a I know because b minus a is my interval. B minus a is 4 minus 1. So I plugged in everything I know. My goal is to solve for x star. What is that special spot on the interval? To solve the left side is to solve an integral. So I need to evaluate the integral from 1 to 4 of x squared dx. I did that here. Remember to evaluate, take its antiderivative, and plug in the upper and lower limits. So the antiderivative of x squared is 1/3 x cubed. I plugged in the 4, and I plugged in the 1. And so that left side eventually simplified down to 63/3. On the right side, 4 minus 1 is 3, and I was just stuck with the 3x star squared until I got to this step. So I didn't show all the intermediate calculations, but basically the 63/3 comes out as 21. And then I divided this 3 over. My goal is to get to this x star. So this comes out as 21. I divide the 3 and got 7. So I know that x star squared is 7. That implies that x star is radical 7. Now, technically, I get plus or minus radical 7, but negative radical 7 isn't on the interval, so I ignored it. But technically, you get 2 answers for that. But I'm negative radical 7's outside that 1 to 4 interval. So this is the spot that fulfills the mean value theorem for integrals. And then I tried to draw a little picture on the right to show what the property this spot has. Basically, if you calculate the area from 1 to 4 under x squared, you get this number 21. The mean value theorem for integrals says there's some spot on the interval that if you just take its height times the width, now the height of radical 7 is here, it's radical 7 squared, which is 7. So basically, this rectangle is 3 by 7. So this 3 by 7 has an area of 21. It matches the area that's under the curve here, which is also 21. So that spot is what the mean value theorem was talking about. Now, the mean value theorem told me that spot existed. It didn't tell me what spot it was, but by using the formula, I could find it. So the x star, the spot that fulfills the mean value theorem for integrals, that basically the spot that makes this rectangle the same as the area under the function, is the spot radical 7. And radical 7 is on the interval. Clearly, whatever I find, there must be at least one spot on the interval. Radical 7 is greater than 2 and less than 3, so it's somewhere between 2 and 3. So it's definitely on the interval from 1 to 4. So if you're asked something like this, it's basically just plugging into this theorem and or in this equation from the theorem and finding what value fulfills it. Conceptually, you're supposed to know that there is some such value, and that's what the theorem states. There is a way to find it if you want to go through and do the work. All right, so this just shows the mean value theorem for integrals. I'm going to make a second video that will show how we use this, and its big application is to find the average value of a function. All right, so look for the second video after this.